Welcome to the Foundry by Forge College. Grab your technical pens because today we're rolling out the blueprints for our next explainer, cross-program invocation patterns. Now, as we continue our journey through programming with Anchor, right here inside the Anchor Framework Essentials track, we're really expanding our Solana development toolkit. Last time out, we mastered event handling and logs, right? But today is where things get super interactive.
So think about this for a second. What actually happens when your program needs a favor from another program? I mean, in our previous lesson on event handling, we were safe inside our own house. We knew exactly where everything was, and emitting our own logs was a breeze. But now we're stepping outside. We're literally crossing the street to ask another, completely independent program to execute an instruction for us. And as you can probably guess, they aren't just going to let us waltz in without checking our credentials.
Here's the blueprint for today. 1. Programs talking to programs. 2. The 3 bureaucratic rules. 3. Constructing your CPI context. 4. Debugging common CPI failures. And 5. Creating your debug report. Let's jump in.
Section 1. Programs talking to programs and the explicit reality of CPIs.
So, by definition, a cross-program invocation, or a CPI, happens when your program executes an instruction that belongs to another completely separate program. I kind of want you to picture this other program as a heavily caffeinated, incredibly strict bureaucrat. You know the type. They don't know you, they don't inherently trust you, and they will absolutely check every single line of your paperwork before letting you do anything. You can't just slide up and say, "Trust me, I'm good for it." Nope, you have to prove it.
Just look at the contrast here. On the left, we've got your local invocations. Back when you invoked your own handlers, ownership and signer expectations were implicit. It was local, it was easy. But over on the right, we have CPIs. A CPI requires totally explicit mapping. You have to actively assert which accounts are writable, which are signers, and who actually owns the underlying data. Because that other program, it's going to deserialize those accounts and double-check your math. Honestly, mismanaging these explicit expectations is the root cause of almost every single CPI failure you're ever going to run into.
Moving on to Section 2. The 3 bureaucratic rules, or how to get past the callee's bouncer.
Okay, so you need an exact dossier to get through the door. First up is the what. The callee is checking account type and mutability. Like, are you even allowed to edit this thing? We handle this in Anchor with the mute macro. Second is the who. This is all about signer semantics. Who is actually authorizing this action? The callee tricks the is signer bits and has one relationships to verify your identity. And third, the how. Exactly how is this invocation being packaged? We use CpiContext for that. What, who, how. You must prove what you're editing, who's authorizing it, and how the whole thing is packaged. Leave even one of those blank, request denied.
And if you do fail any of those checks, bam, you get hit with one of these classic rejection stamps. We're talking wrong owner, missing signer, or not writable. If our strict bureaucrat spots any of these missing from your explicit declarations, they will immediately panic your transaction. Seriously, no second chances, just a hard error. So, how do we avoid getting stamped?
That brings us to Section 3, constructing your CPI context, drafting the architectural blueprint.
All right, the absolutely crucial point here is the to-account info method. You're going to see this everywhere in your CPI invocation code. Why do we need it? Because you have to map your account data into the raw format the callee expects to deserialize. Think of it like translating your messy internal notes into the perfectly standardized dark green ink forms the global bureaucrat demands. If you pass an account that isn't owned by the callee program at runtime, their deserialization process is going to fail right then and there.
Now check this out. On the left, we've got CpiContext.new. You use this for your standard accounts that have explicit external signers. Super straightforward. But on the right, this is where things get fun. CpiContext.new with signer. When you're dealing with program-derived addresses, or PDAs, you don't actually have a private key to sign with, right? So you must use new with signer to legally forge, and yes, I mean legally forge, the required signatures using your bump seeds. It basically tells the callee, hey, look, I have the mathematical proof to act on behalf of this address. Which leads nicely into Section 4, debugging common CPI failures, when you get ghosted by another program.
Okay, listen up, because you should always follow these 4 steps sequentially. 1. Reproduce the issue locally using Anchor test. 2. Inspect your validator logs to find out exactly why you were rejected. 3. Apply a minimal, targeted code fix. And 4. Verify the successful output.
I can't stress this enough. You should always reproduce the failure safely on your local validator before you even think about touching mainnet code. It saves time, it saves money, and honestly, it saves your sanity.
When you are digging into those local validator logs, these are the specific, kind of terrifying warning codes you want to hunt for. Account not writable, that's an access violation. Account owned by wrong program, that's a deserialization failure, meaning you brought the totally wrong account to the party. And oh, this one is an absolute classic. Custom program error 0x1. That obscure little hex code just means you have a missing is-signer authorization. Pinpointing the exact error tells you exactly which of our 3 bureaucratic rules you ended up violating.
The good news? Once you know the rule you broke, the fix is usually tiny. A beautifully targeted fix, like carefully passing in your PDA signer seeds right here, is often literally all it takes. By supplying the exact bump seeds the program expects, you turn a strict bureaucratic denial into a successful increment. And let me tell you, it is incredibly satisfying when that finally clicks into place.
And our final section, number 5, creating your debug report, assembling the final dossier.
To wrap this process up, your final debug report really needs to include these 5 elements. You got to have the initial failing logs, a brief explanation of the root cause, the exact code patch you applied, the final passing logs to actually prove it worked, and a quick note on future account management rules. By writing this down, you are transforming a super frustrating, time-consuming error into a permanent, reusable checklist for your next multi-instruction transaction. You are quite literally writing a manual for your future self.
Which brings us to our core takeaway for today's explainer. Trust is implicit locally, but explicit globally. While our local event handling was this cozy little environment where you made all the rules, CPIs require absolute, surgical precision and explicitly declared expectations. You have to prove what you're editing, exactly who you are, and how you're invoking the call. Always check the paperwork before you cross the street to talk to another program.
To dive deeper into these schematics and explore more advanced Solana development topics, make sure you visit forge.college. So, as you stare down your own smart contracts today, ask yourself, what massive favor is your program going to ask for next? And is your paperwork completely, perfectly ready? Thanks for joining me on this explainer, and I'll catch you in the next one.